introduce Professor Akinlabi, Professor, University of Johannesburg. She is a professor at the Department of Mechanical Engineering Science, Faculty of Engineering and Built Environment, University of Johannesburg. Her research interests are in the field of modern and advanced manufacturing process, friction stir welding, and additive manufacturing. He is a rated National Research Foundation (NRF) researcher and has demonstrated excellence in all fields of endeavors. He is a member of prestigious South African Young Academy. He is a South African Young Academy of Science and registered with the Engineering Council of South Africa. She has filed 2 patents, edited 1 book, published 4 books, and co-authored over 250 peer-reviewed publications. He is a member of prestigious South African Young Academy of Science and registered. Welcome you, ma'am. Welcome you, ma'am.
Thank you, Dr. Tanya. Good day to everyone. And for me from Johannesburg, I will say good morning. This is about 10:30. In India, it is good afternoon because you are at 2 p.m. already. Thank you very much to Dr. Taya, and I would like to start to also seize this opportunity to thank Prof. Swadesh Singh, who has been my collaborator for a number of years, and who is the person that contacted me, and he's the one, the brain behind this program. And thank you very much to Prof. Singh, and to other committee members as well, to be able to put this online development program together. I want to start by commending your effort to be able to achieve this feat. Looking at my screen from here, I see 411 participants. This is a huge number, and I'm really wondering how you were able to pull such a number together amidst the lockdown and everyone facing one challenge or the other. And however, the COVID-19 pandemic has really enabled us to learn and unlearn, and we are really taking challenges. We are pulling on and moving forward, irrespective of the pandemic across the globe. And I think that I will again have some insights into a couple of slides that I've put together to share with you from my research experience this morning. I will now move ahead to share my screen. All right, so I'm now sharing my screen, and the topic before me is a characterization of weldments, and in particular, from my research experience in the field of friction stir welding and friction stir processing. This is an FDP program with the theme Recent Advances in Materials Characterizations. This is the outline of my presentation. I will start with the introduction into the field of welding, generally. Then I will narrow into the friction stir welding technology. I will share with you some benefits and applications. From there, I will move on to highlight how we can ascertain joint integrities, particularly in the field of friction stir welding. I will then present some materials characterizations with a case study of aluminum and copper, dissimilar welds. And lastly, I will share some work that my team and I have done in the field of friction stir processing. Joining of materials is believed to have started around 1000 BC in Greece. And they started by having to produce jewelries. Greece jewelries are known to be very famous, ancient, and many people still value them till today. And in that technological advancement from Greece, they were able to produce jewelries, and this was used in Greece and later on shipped to other parts of the world. The history around joining, as we all, for India, when I checked the history of how long welding had been used in India, dates back to so many years as well, thousands of years ago. And I came across a particular interesting, the Iron Pillar of Delhi in India, that this was built by using the welding technology in 310 AD. On the African continent, I saw the Egyptian soldering of the golden death mask that was the welding technology was used in 1330 BC. However, welding technology remained primitive until the advent of the first industrial revolution in the 1700 to 1800. And you will agree with me that almost every fabricated item that you can think about at home, in the office, in industries, and all over the world will always contain one form of joining, and welding technology has been in the forefront of the ability of manufacturers to be able to join two materials together. With this background, in general, civilization and welding started with copper and then progressed to bronze, silver, gold, and iron across in the manufacturing industries. But then, over the years, with the advent of the second industrial revolution, the third, the fourth, and even the fifth industrial revolution, currently in Japan, we then realize that welding technology have now been used in joining metals, plastics, composites, and so many materials globally. Hence, the importance of welding technology, and more so, the importance of researchers knowing fully how to characterize the welds to be able to ascertain the joint integrity. With this background, still on background, classification of welding, I'm not sure how many of us participants are very familiar with this particular field. I've put this slide here, but I will try not to bore you. Having the general classification of welding into fusion welding technologies, which is the conventional welding technologies, and the solid state welding technologies. And under the fusion welding, we have the metal inert gas welding, the TIG, the MIG, TIG, the laser beam welding, and under the solid state welding, where we have the friction stir welding. We also have other welding technologies like the friction welding, the ultrasonic welding, resistance welding, and so on and so forth. Now, narrowing down to the friction stir welding technology that I have been able to work on and contributed in the last, I've been working on in the field of friction stir welding since 2008, over the last 12, 13 years. This technology was invented by Dr. Wayne Thomas of the Welding Institute in the UK in 1991. It is a solid state welding process, as I mentioned earlier on. It's a process wherein we plunge a tool into two abutting faces of two materials to be joined. The materials could be similar and they could be dissimilar. This technology has been used to join metals, plastics, and composites as well. Over the years, the technology has had a lot of improvement. It is suitable for bat, lap, T-joint, and so many other joint configurations. And the welding temperature is usually between 60 to 80% of the melting temperature of the material, of the base materials. I recalled when I've performed welds using the friction stir welding technologies, I've had opportunity wherein I inserted thermocouples in the welding interface, and temperatures recorded were between 60 and 70% of the melting temperature. Sometimes as well, we've also done some welds wherein we're able to use a thermal camera. That also confirms that the welding temperature is below 80% of the welding temperature is below 80% of the melting temperature of the base materials being joined.
Join in a frictional stir welding.
That was a video showing just for people to understand better the friction stir welding technology. That was it's being used in sealing of engine blocks. Yeah. So furthermore, the technology has proven to be highly beneficial to the industry in the sense that it enhances the evolving properties of the welds are far better when compared to the conventional welding technologies. It can be referred to as a green technology in the sense that during the welding process, there's no film that is given off during the process. No gases are evolved during the process, and you do not even need a nose mask. I can tell you that. Yeah. For all welds I've had to perform on friction stir welding machine, I do not have to use a nose mask as it is today with COVID-19. We use eye goggle in case of debris that could fly off during the welding technology. So no toxic fumes or smoke is produced during the welding process, and hence, when compared to other conventional friction welding technologies, it can be said that the friction stir welding process is highly efficient and environmentally friendly as well. Furthermore, to still on benefits, furthermore, there are, from the literature and also from what I have experienced in working with this particular technology, the technology comes with enormous benefits regarding metallurgical benefits, environmental benefits, and energy benefits as well. So it has low distortion, good dimensional stability, absence of solidification cracking as very common with conventional welding technologies. And for environmental benefit as well, huge as well. No, there's no need for shielding gas, no smoke, eliminates grinding waste and all of that. And it's also beneficial, it has energy benefit as well. In that it has the materials can have improved material use, and it has been proven in the aerospace industry that this technology has led to decrease the fuel consumption in lightweight aircraft, wherein rivets have been replaced with friction stir welding, and that led to reducing the weight of the aircraft. And with the reduction in the weight of the aircraft, that led to a decrease in the fuel consumption. The first friction stir welding commercial application was conducted in the year 2004, and this was tagged as Eclipse 500 business jet, as seen at the left-hand corner of my slide. This was a USA research and development program for the first friction stir welding commercial application, which cost the US government $300 million. And this was done by the Welding in collaboration with the Welding Institute in the UK. I have been privileged to work on collaborative projects with the Welding Institute in Cambridge. The pictures you have there, if you look very closely, you will see me there somewhere in the pictures. These are some of the meetings, workshops, trainings that I have been opportune to do at the Welding Institute. And this particular project was in collaboration with the University of Leicester, which rounded up March 31st, 2020, that we concluded the project. Working, it's industry, academics, industry, and a higher educational institution. Further commercializations of the technology today in Shinkansen trains in Japan. I was opportune to be on the Shinkansen train. That was in 2019, I recall. And I was looking out for the typical application of diffraction stir welding technology. And my understanding is that the friction stir welding technology has been used over many years in Japan to weld the floor panels of the Shinkansen train. This is high-speed train that goes at about 320 kilometers per hour. And this technology has been deployed and used because of its enormous benefits and advantages. Stable, low distortion, and all of that. It's been used in the aerospace industry. Like I mentioned earlier on, so many of the aerospace parts, the wings, wherein there are rivets, have been replaced with friction stir welding technology, with friction stir welds. Also, some parts on the seats, the aircraft seat brackets have also been, friction stir welding technology has also been employed by Boeing to weld seat brackets on planes. And there are some other typical components as well that are patented where friction stir welding technology has been used on the aircraft. That's also been used on the floor panels of the underground tubes in London. So, like I was making a joke that when as an engineer and with the knowledge of friction stir welding technology, when I got to know that all the floor panels of the underground tubes in London were produced using friction stir welding technology. So when the last time I was in London and I was going on the train and I was hearing, please mind the gap between the train and the platform. In my mind, I was telling myself that the floor of what I'm getting onto now got friction stir welding, friction stir welds over there. So other applications include shipbuilding in Japan and also in China. They use friction stir welding technology widely on shipbuilding, and also in the tank container industries as well. I just want to share a little glimpse into how far we are in South Africa and on the African continent. Without doubt, South Africa is in the forefront of championing the friction stir welding technology on the African continent. And I think most of the platforms at the moment are still only in South Africa. I am aware of some other countries trying to also have interest in the technology. And in South Africa, we have some industries are beginning to have interest in the use of friction stir welding technology. And one of them is Eskom, that has also sponsored a project that I've worked on. We have Transnet. I've also worked with Transnet as well in the rail industry. Eskom is the power producing company of South Africa. There's also a tank container industry in Cape Town called GRW. They have been using friction stir welding technology as well over many years. So it's the technology, even though well advanced in Europe, I know that India is also in the forefront of championing so many applications in the field of friction stir welding. for us in Africa, we're getting there. It's gaining traction, a lot of research and development projects, and very few commercializations of the technology that has taken place on the African continent. I have so many collaborators in the field of friction stir welding in India, like IISc Bangalore with Prof. Satish. Prof. Satish. I also have Professor Pal and Prof. Majumdar in IIT Kharagpur. I've been to these places in India, and I have collaborated widely with these two distinguished professors in the field of friction stir welding. And I'm also very happy with the way the friction stir welding platforms, because of the huge cost. I'm happy with so many platforms in India that have been reconfigured from milling machines, and they are doing very, very, very well. So I will now move on now to ascertain joint integrities. There is a need to optimize the friction stir welding process. And this could be quite complex in the sense that there are so many parameters, tool designs that needs to come to play. Considering the friction stir welding processing parameters, the spindle speed, the feed rate, the plunge depth, dwell time, the tool rotational speed, and all of that needs to be optimized. So also the tool designs. There have been so many types of tool designs. The common ones are what I have here. The cylindrical tool with threads, also the one also without thread. The wall tool, the tri-flute, the flat tri-flute, the skew, and then the wrist here. I recall that one of my students some years ago also designed a tool which we were actually trying to patent at that particular point in time, I recall, which we also used to produce some welds, and it actually gave very good flow of the materials being joined. So it performed really well. So there's still a lot of research being conducted in trying to optimize the process. And the optimization of the process parameters and the tool design still remains a challenge in friction stir welding. But then we are getting there. And this aspect as well speaks directly to the joint integrity. The point is that we cannot be talking about having a good weld, materials characterization, without first of all understanding the basic rudiments that needs to be put in place in optimizing the friction stir welding process first. Other aspects that needs to be done to improve the joint integrity of friction stir welds is optimizing the shoulder plunge during the welding process. And this is can be explained through the calculation that I have on the screen now, wherein we calculate the shoulder plunge, which is a 0.5 of d sine theta, where d is the shoulder diameter that is being used, the shoulder diameter of the tool pin that is being used to produce the weld. And then theta, that is the tool tilt angle that is being used to produce the weld. This is to give a rough idea, an estimate of how much we should plunge our tool into the weld during the welding, because this tool shoulder helps with the consolidation of the welds. It helps with enhancing the material flow during the welding process. Hence, this also has to be optimized. On this particular slide, I've shown friction stir welding platforms and automation. The process has been fully automated today. There are so many robotic friction stir welding technology platforms across the globe. And the one on the left-hand side here, that is the friction stir welding platform that we have always used, which is at the Nelson Mandela University at Port Elizabeth, where I did my doctorate here in South Africa. And the other robotic friction stir welding platform you have down at the bottom right-hand corner of my slide, this picture was taken at the TWI in the UK. So the process is fully automated, and it's has been used in various applications today. So ascertaining joint integrity. I've listed here a couple of materials characterizations that can be conducted. This list is inexhaustive. I say inexhaustive because the welds that we're producing has typical application. So the materials characterizations that a researcher wants to do at any point in time will always speak to the typical application of that particular weld. But then there are general guidelines, I would say general, and I will slash it with basic materials characterizations that should be conducted when we are producing welds. Like the first three are very, very basic: the microstructural evaluation, tensile testing, and hardness testing. These three are very basic, and they are our first points of call that we always need to consider when we produce our weld, to be able to see, to know what is happening in the weld in order to ascertain the joint integrity. And then the checklist. A checklist needs to be built by the researcher. If a particular weld will be used in applications wherein fatigue will come to bear, fatigue testing needs to be conducted. Then the researcher also needs to determine when bend tests are required, when corrosion tests are required with respect to welds that will be exposed to various atmospheric temperatures, some environmental conditions and all of that. The X-ray diffraction can be considered. Electrical resistivity measurement when it has electrical applications, residual stress measurement, thermomechanical characterization. This list is inexhaustive. There are so many other materials characterization techniques that have been developed today that are applicable to welds. All we are trying to do is to ascertain the joint integrity of the welds that have been produced. So I will now go ahead to shed a few light on a case study of friction stir welding of aluminum and copper that I have been involved in. Aluminum and copper finds application in bus bars in the electrical industry, and this project was sponsored over many years by Eskom, which is the power generating company in South Africa. The fact still remains that up to today, these two materials, even though they come with huge benefits, they cannot be joined with conventional arc welding techniques. Hence, the application of solid state welding technology like friction stir welding has been considered to join the two materials, either in batch joint or in lab joint. So in this particular field, a lot of research has been conducted from myself and some of my research team members. So I would like to mention some rudiments to joining dissimilar materials using the friction stir welding technology. The position of the tool during the welding process is very, very key and very important. So at the beginning, in dissimilar joining, researchers were not aware of where to actually place the material and also the direction of the tool as well. So I did a fundamental research then in 2008 to ascertain where a particular material should be placed among two dissimilar materials. So in the case of aluminum and copper, if you look at the material, the weld that I'm showing here on the left-hand corner of my slide, you will see weld 069, which has copper on the advancing side, and then aluminum on the retreating side. That is weld 069. While on the right-hand side, I have placed copper on the retreating side and aluminum on the advancing side. You will visibly see the heavy flash and the wormhole that was produced. Now, This is a basic research in trying to determine where and where a particular material should be placed. Now, from this basic research, I did other further welds as well. And then also confirmed from other researchers working in the field of dissimilar friction stir welding. This particular study has been concluded that when we want to join dissimilar materials, the material with the higher melting point should be placed on the advancing side. The notation of advancing side and retreating side, I've shown it on the figure, on the schematic diagram that I have on the right-hand side of my slide. So in dissimilar friction stir welding, dissimilar material joining, the rotation direction of the tool and where we place the materials is very, very significant due to the directional flow of the materials being joined during the process. So this is a basic fundamental research, which I have published. I've mentioned this in one or two papers, and other researchers have also published this as well. And it is expected that, okay, other researchers coming along that need to join the similar materials do not need to go back to the basics of what we have done. This has been done, it's a study done and concluded that to enhance joint integrity, to have a good weld, the material with the higher melting point should be placed on the advancing side of the weld. So it is also expected that for a start, before a researcher even go into conducting the welds, it is expected that the researcher should first of all characterize the parent materials, because you need something to benchmark. You need the parent materials as a benchmarking for a benchmarking. So when we produce the welds, we then have something to benchmark to the parent materials. So we characterize the parent materials individually. It is also expected that we join, first of all, the parent materials as similar materials. For example, when I want to join aluminum to copper, it is expected of me as a researcher to start by joining aluminum to aluminum of that particular grade that I want to join, to also join copper to copper, and then before progressing to come up with my weld metrics. Weld matrices are usually, it's always advisable that before we come up with weld matrices, that we consult the literature to see what people have done in that particular field of study. And then you can use that as a basic to form your own weld metrics to carry on your experiments. It's also important in characterizing welds that we consider the characterizations of the interrelationship between the input and the output friction stir welding processing parameters. I mentioned earlier on an earlier slide, the input processing parameters, the tool rotational speed, the feed rate, the tool plunge, the tool tilt angle, the dwell time, and a couple of them. I think there are 5 or 6 of them that are basic input processing parameters that we need to enter into the welding computer system for welds to be performed. After the welds have been performed, a number of friction stir welding machines are able to give some output data, wherein we are able to analyze the forces acting during the weld. We are able to correlate the joint integrity with the forces acting during the weld. We are also able to have data like torque, and then the forces acting for most friction stir welding machines. We have the forces acting in 3 directions, the X, Y, and the Z forces. We have the spindle torque data, and we are also able to calculate the heat input into the weld. The heat input into the weld is very, very important. It's a very important parameter, as it has been correlated to dictate the quality of the welds. So there are formulas that have been used that are available in the literature to calculate the heat input into the welds. Also, there are so many simulation softwares, mathematical relationships, and softwares that are available in the literature to calculate heat input, also to be able to estimate the welding temperature during the welds. After having looked at the interrelationship between the input and the output processing parameters, it is also expedient to also have the macro appearance of the weld. We section the weld usually at a point where it is stable to be able to have an idea of the welds. At this particular point in time, my team and I have also done a number of, we've also used NDT techniques to ascertain the joint integrity of friction stir welds as well. I think I recall that 1 or 2 papers have been published wherein we highlighted non-destructive techniques, how we have deployed them to ascertain the integrities of friction stir welds. So we then characterize friction stir welds into the stir zone, which is the center of the weld, where we plunge the tool. That is the point where the tool pin has acted during the weld. Further, from the stir zone, we have the thermomechanically affected zone, and then we have the heat affected zone. And then at the extreme, left and right, we have the parent material, as shown in this particular macro appearance. We characterize, this will enable us to see the flow of the material that have been joined during the process. Further to this, we then consider microstructural characterizations. As you can see, we can start with the use of an optical microscope and then progress to the use of SEM. TEM have also been used to characterize microstructural characterization of friction stir welds. And under microstructural characterizations, we also consider the grain sizes as well. We measure grain sizes because it's expected that the stir zone we always have very refined grain sizes if our processing parameters have been very appropriate. So we also we measure the grain sizes across various zones, and we characterize them into various zones, which can be directly correlated to the microstructures of various zones of the welds. We also consider tensile testing. This is a basic one, wherein as a researcher, we consider the yield strength, the UTS, the Young's modulus, and so many other data that we can get from tensile testing. It is also expected that researchers should always consider fracture characterizations in the welds. Now, for welds generally, this particular weld I've shown you on the right-hand side, if you look at it very, very closely, you will observe that this particular weld has fractured just in the TMAZ, in the thermomechanically affected zone. It is expected when welds are characterized, can be given thumbs up, has been good, it is expected that the weld should fracture at the heat affected zone, completely outside of the stir zone and also outside the TMAZ, which is usually an indication that there's a good bonding of the two materials that have been joined. This example I've shown you here, you will see where this particular tensile sample has fractured in the TMAZ, wherein these particular fractured samples were further characterized, and it was found that this particular friction stir welded aluminum and copper has some intermetallics, and intermetallics made the weld brittle, although further details later revealed that the intermetallics in this particular, in most of the welds produced in this study had very low peaks. However, still made the weld to be brittle. Hence, they are not good for structural applications, as the case may be. Further to this, another basic characterizations which we will always conduct is microhardness profiling. The picture on the right-hand side gives typical Vickers microhardness profiling of friction stir welds of aluminum. So when aluminum and its alloys are welded, the steering of the tool during the welding process usually leads to a softening, and this softening then leads to have the hardness of the stir zone as stable. Looking at the plateau that is observed in the right-hand side corner. But if you look at the microhardness profiling on the left-hand side, this is for aluminum and copper. You will see some peaks at the stir zone, which correlates to the intermetallic compounds that are present in the welds. This is X-ray diffraction of dissimilar aluminum and copper weld. If you look at to the top right-hand corner, I have placed in there the various peaks at which these common intermetallic compounds will trigger in the welds. So we have 34,6, 39, and 44,2 for the various intermetallic compounds. Now, looking at the fractal graph, you will observe the very low peaks of two intermetallic compounds that are found in this particular weld. The Al4, the aluminum copper intermetallic compound that is found in the welds. So these further confirm to me that the welds, yes, there were intermetallic compounds, but then they are not, they do not have very high peaks. We can see the low peaks there that have been picked up using the X-ray diffraction. And further test, because we are looking at aluminum and copper, in the electrical and electronics industry application, we had to conduct electrical resistivity measurements to be sure that the welds produced is fit for use. And this was done using the 4-point probe meter. The schematic is placed on the top right-hand corner. We have the voltmeter, the power source, the multimeter, and then we place the sample with the 4-point probe meter, wherein we carefully placed 2 probes on aluminum and 2 probes in the copper, with having the sample of the friction stir welded sample. So this, the result, the data obtained, this is what I have this graph here, which is indicating the electrical resistivity in micro-ohms compared to the heat input into the welds. Because the heat input is correlated, the heat input into the welds is correlated to the formation of the intermetallic compounds, in the sense that intermetallic compounds are formed at high temperatures. So the electrical resistivity was correlated to the heat input to be able to have an idea of what is going on in the welds. We observe from the data that is before us this afternoon, you will observe that the electrical resistivity are very, very low in micro ohms, and that is the data we have here. So with this, we're able to optimize the friction stir welded samples of aluminum and copper And this was used in the electrical industry, in bus bars. So I would like to, the next 1 or 2 slides will speak to, I will highlight some work that we have done in the field of friction stir processing. And this is a variant, the FSP is a variant of the friction stir welding technology. It is also a solid state processing technique that is used to fabricate surface composites as in surface engineering, in trying to modify the surface morphology of materials that has some limitations. The technology has also been used widely to produce metal matrix composites, and these materials have been regarded as advanced engineering materials, and they find applications in the aerospace industries and in the automotive industry. The way this, the way we produce our FSP is that we manufacture grooves in the substrate, the parent material to be used. We have grooves in them, and then we pour powder materials that we want to use to reinforce the surface morphology in the groove. In this particular study, is one of my students that did this study, which I supervised. We used titanium carbide powder, particle size of between 45 and 90 microns. We poured into the groove, and we've then, first of all, use a tool without shoulder to consolidate the particles into the groove. That is what you have there as stage number 2. And we use the tool on the right-hand side corner of my slide, tool designated as A without a tool pin. We first of all use that tool we run that tool with only the shoulder on top of the substrate, the parent material that we want to work on. And after that, we then plunge a second tool, which is tool designated as B in this case. We then use the tool with a pin to perform the friction stir processing. And this particular study was aimed at improving the wear properties of aluminum alloy. We observed that because of the ceramic nature of TIC, these greatly improved the properties, the wear properties of the aluminum material in question in this particular study. So several other material characterizations were also conducted as well. But our most priority in this particular study is the wear study. And that is why I've shown you the 2 wear tracks that we got from this particular study. In another study, also producing aluminum metal matrix composite, this time around with a titanium alloy, we follow the same process as well, to have titanium alloy grade 5 to enhance the strength to weight property of the aluminum material, and this improved greatly the strength of the material that was produced. You will see the microstructure taken with the same, how it's showing an even distribution of particles and very refined grain structure of the aluminum and titanium particles at the stir zone of diffraction stir processed aluminum metal matrix composite. This study was also very successful, was published, and we're also considering some applications as well for this particular study. I've also shown here on the bottom right-hand side corner of my slide some of the tensile results showing the ductile behavior of the diffraction stir processed aluminum MMC. Okay. Now, still on materials characterization generally, there are so many other materials characterization techniques that have been developed, that have also been used, and many are still being developed. So a student of mine also did some work wherein we used molecular dynamics, applied it to quantify the strength, the outcome of diffraction stir processing of aluminum 6061. So these are some of the outcomes of that study. Now, other weld characterizations that are also widely used by researchers is to consider statistical analysis, various software, design experts, and so many other software that are available in the open literature that can be used to characterize welds. There are also so many numerical simulations using FEM, many softwares that have also been used to characterize welds. And also there are opportunities for a lot of researchers also go into mathematical analysis. And for me and my research team, we have been, I would say, 85 to 90% experimental, within a little bit of, experimental and statistical analysis. That's the core of what we do in my research team. A lot of our, majority of our work we do, we conduct materials characterizations through experiments, and we also conduct statistical analysis as well. And then a few students have delved into numerical simulations using software, like this one student that used molecular dynamics. I've also had one student as well who used the ANSYS and a couple of other work as well, but still at developmental stage. I will not consider myself as an expert in numerical simulations and mathematical analysis. So, having said that, I'm coming towards the end of my talk. To summarize, I have shared with you this afternoon background and fundamentals of welding generally. In particular, I have shared with you my experience in the field of friction stir welding technology, various benefits, its applications, commercial applications, also at research and development level as well. I've also shared with you how, as researchers, we need to ensure that we ascertain weld joint integrities, and also general materials characterization techniques that we should consider in carrying out weld characterizations. I've shared with you a typical case study of friction stir welding of aluminum and copper, shared with you friction stir processing as a technology, how we have used it in surface engineering to produce aluminum metal matrix composites. And with this background, I believe that you will all agree with me that welding is a technology that will be with us till the end of the age. So, as this particular field of technology, this particular technology will be with us for quite a long time, because we always need to join two materials together. Very, very important. And hence, the field of researchers, the number of researchers in the field of welding generally continues to grow every day. On that, I would like to acknowledge my funders, the Council for Scientific and Industrial Research in South Africa, the Royal Academy of Engineering, the TWI, the University of Johannesburg. I've received some fellows from the Carnegie African Diaspora. I've had some funding, a lot of funding from the National Research Foundation in South Africa. Also some funding from the National Science Foundation in the US, from ESCOM as well, and a couple of other funding bodies that have contributed to my research in the last 11 years that I've been working as a faculty member. I would also like, anytime I make presentations, I like to always acknowledge my wonderful team members. I have a very large research group at the University of Johannesburg, many master's, PhD, and doctorate studies that work in the research team to give the necessary support and to help one another. And this particular slide, I've been privileged to co-author 6 books in the field of friction stir welding, in the field of laser additive manufacturing, functionally graded materials, bamboo, and also non-contact welding and joining technologies, and all of that. All these books are available on Amazon. If you are interested in any of them, if you search in the Google Esther Akinlabi books, you come across a number of them, 6 of them. They are all available on via Amazon and many other book Springer as well, and many other book stores. And on that note, I would like to conclude by saying thank you to you all. Now I see 524 participants on board. This is really amazing. You have my email address here.